Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at Statistics 1, Distributions, Part 1, Binomial. So in this unit, we're getting into several different distribution formulas. And the first one that we're going to look at is the binomial. So the binomial and the next one, the geometric, both of them work with discrete data, as opposed to the normal distribution works with continuous data. So one of the first things that you want to look at in a distribution problem is to look at the data and determine whether it's discrete or continuous. That's going to be one of your clues as to which distribution formula that you're going to work with. So for the binomial distribution, you're going to work with discrete data, meaning only specific values within a range, are acceptable. So you might say, why do we need a distribution formula? In the previous video, we looked at probability distribution tables where we were very well able to manually write out the distribution chart, the distribution table. We were able to generate that ourselves off of a tree diagram. But remember, our tree diagrams generally don't go beyond 3 trials. So in other words, you have your first branch is the first trial, then your second branch is the second trial. Normally we don't go we usually go only up to about 3 branches before we stop. After that, it gets a little too big to manage. So when your number of trials exceed probably 3 or 4, it then becomes burdensome to do it manually. And so we have nice formulas to help us figure out probability without having to draw an enormous tree diagram. So that's what the binomial distribution formula is going to help us with. There are several criteria that you need to memorize. Every once in a while, the Cambridge question type will ask for criteria or reasons for why you can use binomial distribution. So it's good for you to memorize all 4. Usually they won't ask you for all 4 at the same time. They might ask for like 3 out of the 4. And so, but it's very important that you learn this criteria, especially the first one, okay? So again, when you get to a distribution question in a Cambridge exam, the first thing you want to look at is the data, discrete or continuous. If it's discrete, it will either be binomial or geometric, and if it's continuous, it will be normal distribution. The second thing that you want to look at, if it's discrete, you want to look at the criteria. And there's a difference between the binomial and the geometric with respect to the number of trials. For binomial, it's a fixed number of trials. For the geometric, it's not fixed. In other words, you keep going until you find a success. Whereas in binomial, you have a set number of trials, and out of that set number of trials, you have so many successes and so many failures. So in the geometric, you're going to keep going until you have your first success. So this first one is important in distinguishing between the binomial and geometric. So there's a fixed number of trials, n. So where you see the n's up here, all the n's are the fixed number of trials that you have. Your trials are independent, meaning one trial is not affected by the previous one. This one you pretty much can take for granted. Cambridge doesn't really ask you to do too much thinking with respect to that, although it should be pretty obvious from the question that the trials are independent. Then number 3, you only have 2 possible outcomes, and that is success or failure. Again, this isn't one that you should have to think too much about. And I should point out that when it says 2 possible outcomes, it means you can also group it into a success and group all the rest into failure. What I mean is, let's say you're rolling a die. So a die has 1, 2, 3, 4, 5, 6, and your success is rolling a 5. Well, your 5 becomes your success, and all the others become the failure. So you can just say not 5. So you might think, well, there's more than 2 possible outcomes in rolling a die. But what you're looking at is not the number of possible numbers from rolling it, but can you group it into success and failure, which generally, again, you can. Like I say, you don't have to think too much about it, but you still need to know the criteria. So again, you'll have a clear success and everything else being failure. So it might mean for the failure, you have to add up all the probabilities of the non-5s to get your failure, or do 1 minus the probability of 5. Okay, so that's number 3. Number 4, again, relates to number 2, and that is your probability of success, which is denoted by the letter P up here. Your probability of success is constant, which again is indicative that your trials are independent. If your trials are not independent, that's when your probability changes. So again, numbers 2, 3, and 4, you're not really going to have to do too much thinking about it, other than remembering these 4 criterias. These last 3 are pretty much generally understood. It's this first one that's going to determine whether you use binomial or geometric, and also being able to identify discrete versus continuous. So those are the ones that you're going to want to make sure you have set in your mind, and the other 3 you can just memorize. So let me get this out of our way. Now, when you have determined that your question involves binomial distribution, it's a good habit to start proper notation now, because you're going to learn 4 different distribution methods in total. We're starting the first one. So having good notation, first of all, identifies properly the type of distribution you're using, and it also identifies the parameters, that is the important data points that you need to be successful in the problem. So this up here is your proper notation for a binomial distribution. Remember the capital letter X. We saw this back in our probability distribution table video, that the capital X represents your random variable, whatever it is that you're looking for the probability of success about in the problem. So this is your random variable. This little squiggly line, I don't really know its technical name, but it basically stands for distribution. So your random variable is distributed. So you're going to use that little squiggly line. And then you use a capital B to represent binomial distribution. And then you have parentheses with 2 numbers and a comma in between. So these 2 numbers are your parameters, the alongside measurements that you will need in being successful in this question type. The N, as we saw over here, is the number of trials that you're dealing with. So remember when we did a tree diagram, if we only had 2 branch sets, that basically represented 2 trials. Well, now you might have 10 or 15 trials, which obviously we can't do in a tree diagram. So that N is the number of trials and the P is the probability of success. Notice off to the side, I put a Q in red, and that Q represents our probability of failure. So you actually can calculate Q by 1 minus P. Remember, 1 represents 100% of your probability. So if you know the success, you can subtract it from 1 and automatically you have the failure. So even though it's not one of the parameters, it's still an important piece of information that you will need in the formula, as you see that it shows up a couple of times. Now, this is in your Cambridge formula sheet. All of this information right here is in your Cambridge formula sheet. So technically, you don't have to memorize it. However, you should become comfortable enough using it that you don't need the formula sheet. Remember, every time you have to refer to the formula sheet, it takes time. Now, if you forget, yes, use the formula sheet. Definitely look it up. If you're doubting, look it up to make sure it's correct. But really, you should become familiar with this enough to get away from the formula sheet. So this is your way, your notation, your proper way of writing it. This is what you should write first. This over here is your formula. So the probability, where R represents the number of successes out of all of those trials, however many trials there are, there's going to be a certain number of successes. To calculate that equals, here's the formula. We've seen the N over R before. This is Pascal's notation. And remember, this is the NCR key, not the NPR. This is not NPR. This is probability. This is a little p, not a capital P. Probability for a certain number of successes. So this is your NCR key. Let me just put that here if you want to put it in your notes, because that's how it's written in the formula sheet. P is your probability of success, and the R again represents how many successes you have. So that would be, again, if you have 3 successes, then that's your probability of success cubed, because you multiply your probability as you go through your tree diagram. So P to the R, and then Q is your failure, and N minus R, well, if you have 10 trials and 3 are success, then that means 10 minus 3 or 7 failures. So this is just N minus R. Those two numbers, the exponent of the P and the exponent of the Q, have to add up to N, the number of trials. So this is your formula for figuring out that particular probability. These two formulas over here are, again, as we go through statistics, you're going to find information being displayed in different formats. So now our information is displayed like this instead of in a probability distribution table. So that means we need a different way for finding mean, variance, and standard deviation. So the mu is the same thing as mean. Okay, so you've seen the x with the bar over it, mean. You've also seen e to the x, which is expected mean. Now you see the mu. So mu from here on out is also going to represent mean. And to find the mean, it's really easy. You just multiply n times p. N is the number of trials. P is your probability of success. And so that's going to give you your mean. And then to find variance, remember sigma by itself, this is the lowercase s in Greek. This sigma by itself is standard deviation. But when it's squared, it's variance. Because remember, sigma equals the square root of the variance. So if you want to find variance, you square both sides and your sigma ends up squared. So this is actually variance, var x, the same thing that we use these two in the probability distribution table. So now again, our information is in a different format. So we need to adjust our formula. And so variance is NPQ. Again, it's pretty easy because we already have this information available. So if you want standard deviation, then you have to square root the NPQ. So those are our important statistical information for location, that is mean is a location representing a data set, and spread, how far the data set is spread from the middle. Then, again, this was the notation, and this is the formula. So these are the important mental aspects of the binomial distribution. So let's set up our first relatively straightforward problem and look at how the mechanics of it works out. Okay, let's look at our first problem. So screen share here and look at our first problem. It says, in a certain country, the probability that a child owns a bicycle is 0.65. Then in the first part of the question, it says a random sample of 15 children from this country is chosen. So a sample is chosen, 15 children. Find the probability that more than 12 own a bicycle. Okay, so out of 15 children, more than 12. Okay, let's go back to the board and think about this here just a second. So our random variable are children. First question, is it discrete or is it continuous? Hopefully this is obvious. Number of children are discrete. You can only take specific values. In fact, children follow positive integers. Or you could say 0 children. So 0, basically the whole numbers, 0, 1, 2, 3. You don't have negative number of children and you don't have half a child. So it's obviously not continuous. So it's discrete because it can only take, children can only take specific values, being our whole numbers, 0, and in the positive integer direction. So that's the first thing you want to do. Then you want to look at is it a fixed number of trials, or are you continuing to take children until you find one that owns a bicycle, being your first success? This gives us 15 children. So that is a fixed number of trials, meaning we're going to use binomial distribution as opposed to geometric distribution. So the first question, discrete or continuous, that separates between binomial, geometric, and normal distribution. And then fixed number of trials makes it binomial as opposed to geometric. Okay, so here's our fixed, this is our n. And this is what we need to find, the probability that there's more than 12. So let's do this right. Let's start with proper notation. Again, as you start adding more probability, it's important you develop a good habit of writing your notation correctly. It will help guide you. You can reflect back on it in the problem. So what we want to put is x, our random variable, is distributed binomially. Fixed number of trials is 15, and our probability success, it says that these own a bicycle, so that's 0.65. Those are the parameters. And then I just put on the side the Q. So if 0.65 is the success, then 0.35 is the failure. In fact, you could put Q equals that's a Q, by the way, Q 0.35. 1 minus 0.65 is 0.35. I just put it there on the side. By the way, the Q can also be replaced with 1 minus P. I believe in the Cambridge formula sheet, instead of putting NPQ, they actually put NP times 1 minus P. 1 minus P and Q are the same thing. So I like to put NPQ, but realize that Q is the same thing as 1 minus P. So this is the proper notation. Now let's figure out, what does the question want? Well, the question wants the probability that our random variable is more than 12, okay? So more than means greater than, and it doesn't have the equal to. Very important with binomial, because binomial is discrete. So greater than 12. That's what we're looking for. The probability that the number of children that were selected out of 15 are greater than 12 own a bicycle. So this is something to write in your notes about binomial distribution. Pay attention to the inequality, whether it includes or does not include the equal sign, because it's discrete. Meaning if it does not include the equal sign, you have to move on to the next number. So this is the same, okay, this is the same as the probability that X equals 13, 14, and 15, okay? So why did I do that? Well, if you go X greater than 12, then that means you have to start at 0. No children own a bicycle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means you have to do this formula 13 times because you're starting at 0. That's a lot. Or, and sorry, I should put here, very important, not, no, this is correct. Greater than 12 is 13, 14, 15. Make sure you're paying attention. If you are doing the same thing, you put it like this. And if you're doing the opposite, then you would put not. So we'll see that in a further example. But for this one, greater than 12 is 13, 14, and 15. So instead of we don't want to do 0 through 13 to get up to 12. So it's easier to do the other side, 13, 14, and 15, which is our greater than 12. And notice it does not start with 12 because there's no equal sign. So the next integer is 13. Okay, so that's the important part. Pay attention to the equal sign or not equal sign. And so you start with 13, 14, and 15 up to n. This is the same thing as this, okay? So now we are doing 3 formulas, 3 of these, 1 for each number. So that looks like this. We use NCR, so we have 15, C, 13. Our probability of success is 0.65, and this represents 13 successes. That means 13 children that have a bicycle, and 0.35 or 2 failures, meaning 2 of the selected do not have a bicycle, plus each one of these represent a different pathway. If you were to do a giant tree diagram with 15 branch sets, each one of these would basically represent a different pathway. So we need to add them together. This is like looking at the end vertically, and we're seeing the pathway that ends up with 13, the pathway that ends up with 14, the pathways, all the pathways that end up with 15, and so we're adding them up together. So this is now 15C14, 0.65, 14, because there's now 14 successes, 1 failure, plus, and I'll just put it down here, 15C15, where all of them are success, and of course, no failures. I'll still write it anyway, just so that you see the consistency, equals, now if you calculate this one here on your calculator, so be careful when you calculate this. Take your calculator, work it through, make sure you're getting the right numbers. So NCR times 0.65 raised to the 13 power times 0.35 squared. And what you should end up with is 0.047555. I like to write lots of numbers just to make sure my accuracy. You probably could round this one here off to a 6. If you want to end up with accuracy of 3 significant figures, you should put 4 significant figures in your work. So I could have actually stopped here and put this one as a 6 plus 0.012. And by the way, I never put zeros in front of my decimal places. Very rarely do I put zeros in front of it. So be careful if you're looking at my work. This 0 is after the decimal point, not before the decimal point. Okay, so I don't know if your teacher happens to be picky on that, but I don't put zeros in front of my decimal points. To me, it's kind of just a wasted number out there. The decimal is self-explanatory. So 617, okay, that's a 7 there, plus 0.001562. And when you add all those 3 up, and by the way, you can put all of this into your calculator all at once. As long as you don't have too many of these, your calculator will hold it in the memory enough, at least for 3 should be fine. And you get all of this together at once, and you should end up with 0.0617, 0.0617. That is accurate to 3 significant figures. Remember, zeros on the left are never significant. Zeros in between other digits are always significant, and zeros on the right are only significant if a decimal is expressed. So that's your way of figuring out significant figures. So since this 0 is on the left, it's not significant. So 6, 1, and 7 are the 3 significant figures. Obviously, 7 is rounded, one way or the other, it's rounded. And so these are the values that you should get. So notice you need to do a separate formula for each value that you're finding in the probability, but this is definitely a lot easier than if you had to draw out a 15 branch probability or tree diagram. You would still be working on the tree diagram. Okay, so this is the straightforward one. Now let's move on and look at a different way of doing this problem. Okay, let's look at our second example here. And we see it says a competition is taking place between 2 choirs, the notes and the classics. There is a large audience for the competition. 30% of the audience are notes supporters. That is, the 30% of the people in the audience like the choir called the notes, and 45% of the audience support the choir named the classics. The rest of the audience are not supporters of either one, and no one in the audience supports both of the choirs. So a random sample of 6 people is chosen. The sample is chosen, has 6 people from the audience. Find the probability that no more than 2 of the 6 are notes supporters. Okay, so 6 people chosen. Find the probability that no more than 2 of the 6 are notes supporters. So let's think about that carefully here. First of all, these are, again, people chosen from the audience. So that's obviously discrete. And then the number of trials, there are 6 people chosen. Okay, so again, we're dealing with fixed number of trials. So make sure mentally you prepare yourself to work your way through these questions before you just jump in and try to, solve, because you're going to be dealing with 4 different types of distribution, and it'll be easy to get confused later on. So since this is our first one, there's really nothing to confuse it with yet. So first of all, it's discrete. Number of people from the audience. Then from the criteria, we're dealing with a fixed number of people that were selected, 6. So our N equals 6. And these are notes supporters. Okay. So what we want to do is first make our proper notation. Our random variable is distributed binomially because it's discrete and fixed number of trials. Again, don't forget to memorize these other ones. It's still important to memorize them, even though you don't really have to think about them too deeply. So then our number of trials is 6. How about the probability of success? Well, if you're a notes supporter, then that means 30%, don't forget to change it to a decimal, so 0.3, which means our Q, or the failure, is 0.7. So 0.7, or 70% of the audience, does not follow the notes, do not support the notes. Now you want to make your probability statement. So the probability that X, and it says that it is at least 2 of the 6, at least 2 of the 6. That means your probability is, or was it at most 2 of the 6? Let's check really quick. Want to make sure we have our probability the right way. Oh, no more than 2. Okay, so make sure you're careful. No more than 2. So if it says no more than 2, then that means it's going to be less than or equal to 2. No more than means it can be 2. So less than or equal to 2 for that. So this means that our probability can be, the probability of X can equal 0. And again, don't forget 0 is an option. You can have no supporters out of your 6 selected people from the audience. Maybe none of them support the notes. So 0, 1, or 2. So it's important that you make out your list so you know how many times you have to do your formula. So N less than or equal to 2 is the same thing as 0, 1, and 2. Okay, now let's set up our formula here. So we have N6C0, meaning there were none. Probability of success is 0.3, and we have 0 of those in this particular one. 0.7 then has 6, so 6 failures, plus 6C1, 0.3, with 1 success 0.7, then now has 5 failures. So don't forget to adjust your exponents as you go. Plus 6C2, 0.3 now has 2 success and 4 failures. So here's setting up your formula. By the way, if you do it you can put it all in your calculator at once, but you need to be careful because if you just make one mistake, of course, it makes your answer incorrect. If you're following by looking at a mark scheme, at least if you do it separately, I don't know if the mark scheme will list out every number or not, maybe not. So you might want to do it separately so you can find a mistake if you make one. If you do it separately, you don't have to retype it in each time. Once you type it in once and write down the number, then just go back and change your R, this exponent, and this exponent. So everything else stays the same. Just change it from 006 to 115, calculate it, then go back with your arrow key and change the 115 to 224. And that way you can do it more quickly, more efficiently, instead of retyping every time. So learn how to use your arrow key and your calculator efficiently when you're doing this. So when you solve this one, you should end up with, and I'm just going to give you, for the sake of saving us some time, you calculate this all out, whether you write it down separately or as one value, you're going to get a final answer of 0.744. 0.744. In other words, a 74% chance that if you select 6 people from the audience, that no more than 2 are supporters of the choir group, the Notes, is what that means. Now let's go back and look at the second part of the question. Second part of the question now says, find the probability that none of the 6 people support either of these choirs. Okay, so none of the 6 don't support either one. So that's going to be our don't. They don't support either one. I called it D, N for note, C for classic, and then the other 25% don't support either one. So in this case, our IA, maybe I'll put it in black here, our IB, this one was IA, IB, we still have 6. But now, and really, you don't have to rewrite your distribution because it's really the same question. It's using the same information. If it were making a change to the information as far as your parameters, then I would rewrite this statement. But since it's already still the 6 people, still the same percentages, and it's still binomial, this still applies. So you can use this one right here. The X is distributed, but we need to change our probability statement. So now we're looking at the probability that the X chosen equals 0, that there's no supporters. So when we go to write this out, we're going to have 6 choose 6. Our 6 successes are going to be the failures. So, or are not our failures, but the ones that don't support either one. So our 25%, maybe we do need to put the P and Q. You know what, this is based on the notes. You know what, let me go ahead and write a new one because this does change. I didn't think it changed, it does change. So let's write that again so that we have proper information. Again, this shows why you should write the notation, especially if your information changes. We still have 6, but the don't supports is 0.25, means our failures, I'm going to move this 0.744 up here. So our Q is 0.75. Okay. So this is our success. They don't support either one. And our failures is if they actually support one of the groups. Okay, so find the probability that none of the 6 support either group, meaning they don't support a group. That's our success. A failure would be if they do support a group. So this is important. It also helps your mind get a hold of the problem. Now we can write our probability here. Instead of looking at this one, we're now looking at this one here. Again, another reason to write your notation properly. It helps you fill out the formula. Probability of success, all 6 of them are supposed to not support either group. And our failures, there are no failures. None of the 6 actually support a group. Now, there's something that you should note here. First, let me just give you the decimal answer. The decimal answer, if you calculate this, comes out to 0.000244. Remember again, I don't put zeros in front of my decimal. So this is after the decimal, 3 zeros, 244. Very, very slight chance that you could select 6 people from the audience and have none of them actually support one of those choirs. Very, very, very small. It's, you know, basically like a 2.5. Right? If you move the percent back here, it's like 0.02%. Very, very small chance that you wouldn't get a supporter. Now, this is if you just calculated it with the calculator using these notation. One thing you should notice, whenever you have NC0 or NCN, like we do here, 6C6. So if this number on the right is either a 0 or it's the same number as on the left, that means the value of this is 1. That's the left and right hand side of your Pascal's triangle. 1's all the way on the left, 1's all the way on the right. That's because your 0 and the first term of your binomial expansion and the last term, the coefficients are 1. So you should recognize that. You should also recognize that anything to the 0 power is 1. And you should also recognize that 0.25 is the same thing as 1/4. So really what you have is 1/4 to the 6th power. So you could have just calculated 4 to the 6th power and gotten 1/4096. And that is also the same thing, 1/4096. And that's just recognizing that you have 4 to the 6th power in the denominator. So again, these kind of recognitions will be helpful for you in the future. You'll see why in the next example. But if you didn't recognize it and you just calculate it out, this one is perfectly fine as well. Okay, so here we have a 2-part one, and we had to change our notation. At first I thought we didn't have to, but our percentage changed, our success and failure changed because the question changed. This one focused on notes, this one focused on that didn't support either one. So be careful with your notation, and then of course be careful with how you enter it into your calculator so that you get good results. Okay, so one more question, and this next example has a little bit of a twist to it. Okay, let's go to our question and see what we got. Now the first part of the question is pretty straightforward. The probability that Janice will buy an item online in any particular week is 0.35. Janice does not buy more than one item online in a week. So we're looking at 1 week as a unit, and she either buys something online or she does not. If she buys it online, it is a 0.35 or a 35% chance that she does, which means there's a 65% chance that she doesn't buy anything for that particular week. Find the probability that in a 10-week period, Janice buys at most 7 items online. Okay, so let's think through this one. Again, make sure you have your mind situated first. So you see, first of all, it's discrete. Why? Because you're dealing with weeks, and the weeks are either you buy something or you don't. So you're not dealing with half weeks. It's just week and a week and a week, week by week by week. So you're not breaking it up. It's not continuous. So you have 1 week, you have the second week, you have the third week. There's no days in there or half weeks, okay? So it's discrete, only specific values, basically your positive integer values or your whole number values for that. So then, and it's a fixed number of trials because we're dealing with 10 weeks. So we're not looking at how many weeks does she go before she buys something online. We're looking at a 10-week period, and the probability of success in any one of those weeks is 0.35, meaning the probability of failure or she doesn't buy something online is 0.65. So here is our notation, our random variable distributed binomial with 10 trials, 35% chance of success, 65% chance of failure. And it says, find the probability, so don't forget to make your probability statement. Find the probability that online, she buys something online at most 7 weeks. At most means 7 is included and it's the highest number. So you would write this as, and I put ON, I don't want you to confuse the O online with a 0. So online, less than or equal to 7 of those 10 weeks. Well, if we go less than or equal to 7, that's going to be 0, 1, 2, 3, 4, 5, 6, and 7. That's going to be 8 formulas. So you need to, again, when you're looking at the number of trials, you want to figure out which side is the least amount of work for you. So in the previous examples, the way it was fine. For example, we had 12 to 15, so that's 13, 14, 15, because the 12 wasn't included. In the previous one, we had, what was it? Less than 2, less than or equal to 2, so 0, 1, 2 out of 6. So that was the easier one. But in this case, if you go less than or equal to 7, that's 0 to 7, that's 8. So here is where you can use that probability rule that not 8, 9, and 10 means you just do 1 minus the probability of 8, 9, and 10. So less than or equal to 7 is not, or in other words, 1 minus the probability of the online being 8, 9, or 10. So instead of doing 8 formulas, now we only have to do 3 formulas and subtract it from 1. So this is what you want to look at. Again, pay attention to your inequality. Since the equal to includes the 7 here, the 7 is not included over here. So be careful because these are discrete values. So you need to make sure you start with the correct number. I notice a lot of students either make the mistake of not including 0 when they should, or they start with the wrong number because they weren't paying attention to the inequality. So those are important details. Now we can set this up. 1 minus NC, so our N is 10, C8, with the probability of success of 0.35. 8 successes, 2 failures, plus 10C9 with 9 successes and 1 failure, plus, I'll put it down here, 10C10 with all 10 successes and no failures. And this is, again, the not part. That's why I wrote it here, not, and also put 1 minus. So this is 1 minus, and when you calculate all this out, you're going to get 1 minus 0.00482, which equals, and I'm going to write it up here so that gives us a little space down here, or maybe I'll just erase this when we do the second part, and we get 0.995. So there's a 99.5% chance that she will buy something online less than or equal to 7 of those 9 weeks, which makes sense. If there's only a 35% chance she buys something online any given week, the more weeks you have, then of course there's a high percent chance that she won't buy anything online more than 7, 8, or more than 7 times. So there should be a little bit of making sense in the problem to it, but this is the answer. 0.995 is our answer. This one is straightforward. It's the second part that's going to give us the twist. So let's look at that here. Let me screen share. And if we look at the question, it says the probability that Janice buys at least one item online in a period of n weeks is greater than 99%, or 0.99. Find the smallest possible value of n. So what is the probability Janice buys one item, at least one item, in a period of n weeks? Is means it already gives us the answer as far as the probability, greater than 0.99. Find the smallest possible value of n. In other words, we're finding how many weeks, or the smallest number of weeks, still gives us a probability of 0.99 for her buying just one item, or at least one item online. So this one is unique because it gives us the answer to the probability, but now we have to find the number of weeks. So let me erase this real quick and we'll set up the next part. Okay, this is what our notation is going to look like for this one. We still have our random variable of x being distributed binomially, but now we don't know the number of weeks. The number of weeks is n. Our number of trials, it is fixed, but we don't know how many. Our probability of success that she buys something online, still 0.35. Probability of failure, still 0.65. When we write the probability, we now have the answer to it. The probability that our random variable is at least 1. Okay, so at least 1 means greater than or equal to 1. Greater than or equal to 1. At least 1 meaning 1 is the smallest value and goes all the way up to however many weeks there are, and it's going to be greater than 0.99 or greater than 99% probability. So the answer to the probability is actually over here, and this is how you notate it. Sometimes this is called small p here. If you put your answer, technically when you write this out, you could put equals small p, and small p was the answer to the problem that we found out in the previous examples. So now the small p, or the probability, is given to us, and we got to figure out n. Now, obviously, greater than or equal to 1, we don't know how much we're counting up to, but we can count down. So this would be the same thing as not counting down, and we don't include the 0, so not is 1 minus the probability that x equals 0 is going to be greater than 0.99. So I rewrote it because we don't know how far we're counting up to, but we can count down, and there's only one number below 1, and that's 0. You can't have negative weeks. So not is our 1 minus, and then the probability that x equals 0. So we have an equation here, or an inequality here to work with. Now, it might scare you a little bit because our unknown is in a different location than what we're used to, but follow the formula. So now we have 1 minus NC0 times a probability of success of 0.35 to the 0 power, in other words, no successes, and 0.65, how many weeks? Well, it's n weeks, so n minus 0 is n, is greater than 0.99. Now, it looks a little scary because we have these n's in here. But remember, anytime you have NC0 or NCN, that is the right number is a 0 or the right number is the same as the first number, this value is 1. So this cancels out and becomes a 1. And anything to the 0 power also becomes 1. So that cancels out and becomes a 1. So what we really have is 1 minus 0.65 to the n power is greater than 0.99. Now we're getting somewhere. A lot of it canceled out. Now if we add this to the other side to make our n is what we're solving for, to make this term positive, and subtract the 0.99, what we get is, again, we want to make this positive. So we move it to the other side, meaning our inequality is the pointy side is facing the 0.65n. And when we subtract the 0.99 from 1, we get 0.01. And this is where we get to a solution, and I'm not sure why Cambridge does this, because logarithms aren't taught until the P3 book, Pure Math 3. Or, technically it might be in the 2 section of the P3 book, the Pure Math 2. But in other words, it's not in the AS level. So, in some ways, by the mark scheme, they kind of insinuate that you're supposed to figure this out by trial and error. I don't like doing trial and error if there's a very clear way of solving for it. So I'm just going to show you how to do it with logarithms. What you end up doing is you end up taking n is, and I'll explain why here in a second, n is going to be greater than, and what you're going to do is on your calculator, if your calculator has this, you're going to have logarithm, and this one here is the small number in your logarithm, and this number up here is the big number. In other words, you're going to have a log on your calculator. It's going to look like this: log with a box and a box. Okay, so on your calculator, it might be all the way up here in the corner. When you push it, it looks like that. It's all the way up here, this one right here in the corner, and it looks like this. So if you have that key on your calculator, that's the one you want. The little box is the 0.65. It's the base of the exponent. And the big box is the 0.01. So that's what you're going to put in there. If you don't have that, you can also do n greater than log 0.01 divided by log 0.65. If you have a calculator that does not have this key, then use the normal logarithm key which is right here under the 10 to the x, 10 raised to the x. Mine is worn off, you can't see it, but it says log, and there you see log. So this button right here, so you can use that as well, but you have to do log in the numerator and log in the denominator. So this is called a change of base. You're actually using base 10 logarithm instead of this one over here. So either of those will give you the correct answer. Now, the reason why we flip the inequality is because your logarithm of 0.65 is a negative, and when you divide by a negative, it flips the inequality. A lot of students forget to do that. Even if they understand how logarithms work, they forget to change the inequality because they don't realize that your logarithm of that decimal or that less than 1 value is a negative, and so it flips your inequality the other way. But if you can just remember to do this logarithm where the base of your exponent is the little box and this value over here is the big box, and you solve this, you're going to get n greater than 10.69. Don't leave that as your answer. It says find the smallest n. And we're dealing with discrete values. Remember, we're dealing with specific number of weeks. So you can't have a decimal part of a week. And this needs to be greater than that. So even if it said 10.2, don't round down to 10 because it has to be greater than that. The next integer number is 11. So n equals 11. In other words, you have to have at least 11 weeks where she orders at least one value in order to have the probability be above 99%. So like I said, even if this said 10.2, don't round down because it has to be greater than that. We're dealing with discrete values. So you have to go above 10, and the next discrete value above 10 is 11. So n equals 11 is your answer. So write this down here in your notes with respect to logarithms. It will save you doing trial and error and just guessing numbers. You can just calculate it directly using logarithms. Again, this isn't taught until the Pure Math 2-3 book, but it saves you time on the test without having to, plug in a bunch of values. Okay, so I hope that helps. This is our first of 4 different distribution methods that we're going to use. Again, pay close attention to discrete or continuous. Pay close attention. You need to memorize all 4 of these, but specifically fixed number of trials is what makes it binomial as opposed to geometric. These formulas are in your formula sheet. I just realized that we didn't use these at all, and all the examples didn't ask for this. But if it did, if it asked for mean or variance or standard deviation, it's very easy to follow. Again, it's in your formula sheet, and you already got the N and PQ easy information. So those are quite easy to do. You should be able to get those if they ask for it. As always, thank you again for joining me, and look forward to seeing you again next time.